Okay, so this is the function that I just totally made it up. Y'all totally made it up right now. And as you can see on first glimpse, this is what I'm thinking is in your, what I'm hoping, let me rephrase. This is what I'm hoping is in your heads right now. When you first glance at that rational function, my hope is that your gut instinct is like, oh, two vertical asymptotes. Yeah, definitely. Two vertical asymptotes for sure. Because look at the denominator. It has two factors in it. So clearly there should be two error points. One of those error points is at -2 because that's the zero of that factor. The other vertical asymptote is at x equals 5 because that's the zero of that factor. Okay, so you might be tempted to start writing down on your paper, vertical asymptote at x equals -2, vertical asymptote at x equals 5. Okay, and that's all wonderful thought process. Please don't get me wrong. I'm liking where your head's at. But at the same time, guys, when you look at the graph, do you see two vertical breaks in the graph? No, you don't. You only see one. And you can tell just with your eyeballs that the one break seems to be at 5. See that? Look at that beautiful asymptote right there. So there's definitely a break at 5, but there is not a break at -2. And so even if it's not the first thing that comes to your mind, that there might be a hole, I'm hoping that you can at least be on your A game, so to speak, and notice in hindsight that there might be a hole. Because right now I am not seeing two vertical asymptotes. And so if I was tempted to write down that there was two VAs, I would be second guessing that right now if I was, taking a test or something. So now I'm going to look at my function again and I'm going to say, okay, what's going on now? And this is when I would officially acknowledge, oh, but wait a second, there is a factor of x plus 2 in the numerator as well. And since there's a factor of x plus 2 in the numerator as well, that factor on top can reduce out the factor on the bottom. The same way that 7 over 7 equals 1, or 13 over 13 equals 1, or 33 over 33 equals 1. Okay, well, x plus 2 over x plus 2, that reduces out. It reduces to 1 technically. So really, if you simplify that function, it reduces to this. X minus 3 is still on top, and x minus 5 is still on the bottom. But the x plus 2's, they reduce out. Now, check this out. My Desmos has created the new function, you like my little air quotes, new function, in black, and the original function was red. But look at my Desmos. If I turn off the black, oh, hey, there's the red. Turn the new one back on. There he is. Where's the old one? Oh, yeah, there she is. They're the same. Graphically speaking, they look the same. The difference is, of course, the original function is the one that tells you, hey, whoa, wait a second. I have a hole in my graph. There is, we call it a point of discontinuity. There is a point of discontinuity in f of x. We need to know where that point is. So as I was saying in the beginning, you know that that should be at -2 because that's where you were expecting the error to be. -2 is the 0 point of that factor. But again, it's obviously not an asymptote. The graph does not break apart. It's not an asymptote. So what it is, well, we call it a hole. So two things. First of all, I wanted to show you that in Desmos, if you very carefully hold your mouse or your finger, if you're using a touch screen, you can, oh, there it is. If you hold your hand steady enough, there it is. Look at that. It's a hole, y'all. I'm not just making this up. It really is a hole. If you look just to the left or right of it, see how the point is colored in right now? It's like a solid colored in point. But as soon as I hit -2, it goes hollow. It's literally a missing point, literally. So that's why we call it a hole. -2 is undefined. Now, the location though, okay, the location of that ordered pair. Obviously, -2 is undefined, but At the same time, you know, locationally speaking, it does have an output value. Like if I had to eyeball it right now, I can tell that it's not quite at the first, you know, tick mark, so to speak. It's not at -2, 1. No, it's not at -2, 1. Seems to be at -2, I don't know, I'm going to make something up, 0.8, a little bit less, you know, a little bit less than 1. So where though? I would want to know, guys, I'm telling you, I will want to know the location for that point of discontinuity, AKA the hole. So I'm going to show you 2 ways to do it. First of all, if you're using Desmos and if you're being Desmos savvy, as I call it, as soon as you reduce the original function, you can of course graph it in Desmos. Notice I have given him a new name, g of x instead of f of x, because I want Desmos to know that, hey, I'm treating this formula as if it's a new function. Now, you and I know it's the same function, just reduced, but I'm treating it as if it's new. So I've named it G so that my Desmos system knows that it's a new formula. And now I'm just going to ask that new formula, hey, new guy, what if I plug in -2? And guys, Desmos, 0.714. I estimated it to be 0.8. Remember that? Yeah, 714. That's the location of that ordered pair. -2, 714 is the location of that hollowed out point of discontinuity. So if you're Desmos savvy, there you go. That's how you can figure out the point of discontinuity. Of course, I'm a huge fan of algebra. I love me some algebra. So let me do the whiteboard as well, just so that you can see it. So the function after it's been reduced. So let me just go back to the beginning. So here's the original. What was on top? -3. And then the bottom, +2 and -5. Okay, so we know for a fact we have a vertical asymptote at x equals, at x equals 5. And we know that something is going on. I'll leave that blank for a second at x equals -2. So again, you might be tempted to write vertical asymptote at x equals -2, but in hindsight, the graph tells you otherwise, and the formula is trying to tell you otherwise. So if you let those reduce out, now again, when I say reduce out, what I really mean is they divide to be 1. 41 over 41 is 1. X plus 2 over x plus 2 is 1. You would be left with x minus 3 over x minus 5. Okay, so we know that something is going on at the value of -2. We call it a point of discontinuity, AKA a hole. So if you want to know where it is, then you just want to substitute the value -2 in for the function, the simplified function, of course, because don't get me wrong, if I plug -2 into this guy, it's gonna say undefined. Yeah, it's going to say undefined. So you can't plug -2 into the original and find the ordered pair. No, it's going to say undefined. You have to plug -2 into the reduced version. Otherwise, you'll just get an error message. So you plug -2 in for the x's. Numerator, -2 minus 3 is -5. Denominator, -2 minus 5 is -7. So quite frankly, guys, you could just reduce this and say 5/7. Or if you wanted to, as we saw in Desmos, you could divide that out and get 0.714. So what we know is that there is a hole at x equals -2. And now we really know that the point of discontinuity is at -2, 5/7, aka 0.714. Okay, so that was in the PowerPoint, but I got to thinking that I might want to just elaborate a little bit more on that and make sure that it was crystal clear, not only when a hole exists, but also how to find the location of that hole. So that's all I wanted this to be, short and sweet. Hopefully it's helpful. And if you guys have questions per usual, you know where to find me. And I appreciate all of your guys' efforts. And hey, we're almost there. It's like 4 weeks left, maybe less. Yeah, I don't know, crazy. Thank you guys for your time, and we'll talk soon.